Okay, and what I'm going to talk about is actually related to the first problems that he gave it to me when I started working to him. I was, so it was 77. It was at the end of my second year at the university. It was about the random walks, about the entropy random walks, because at that time Anatoly Moiseyevich, he had a pretty broad problem of studying various numerical characteristics of groups describing their behavior at infinity. So, and among those characteristics, of course, well, there are spectral characteristics. Then essentially introduced by him the notion of the Fellner or isoperimetric profile. Then he was also interested at the time in the growth of the Gold-Shafarevich series, but which didn't really quite take off. And then finally the entropy. The entropy, so let me begin with the very beginning, with the history of this notion of entropy, because there is a lot of misattributions there, and I would like to use this opportunity to make it straight. So the entropy is usually, and we heard about it in the previous talk by Professor Pastor. When talking about discrete entropy, this notion is usually associated with the name of Claude Shannon, or sometimes one adds that yes, it was, well, there was physical entropy introduced by Clausius, and then more mathematical one by Boltzmann and Gibbs. However, the truth is that if we are really interested in the entropy of a discrete probability distribution, so here P is a probability distribution with the weights Pi, then this expression, although it does appear in the works of Boltzmann and a bit later Gibbs. However, for neither of them, it wasn't really of any importance, because the entropy they were dealing with in the modern language, it was always a differential entropy, entropy of continuous distributions. And then, well, they had certainly applied certain approximation processes, especially Boltzmann, who was, of course, a physicist, and physicists are much more liberal in passing from discrete to continuous back and forth. So for them, it was just a certain technical expression appearing somewhere in their technical manipulation. So, for instance, Gibbs, he derived what is nowadays called Gibbs inequality, which is non-negativity of the Kullback-Leibler deviation. However, actually, the way it was written, he never imposed the condition that the distributions he was dealing with are probability distributions. So it was just a certain technical lemma. And now the first one for whom this expression, the entropy of a discrete probability distribution, was really conceptually significant. The first one actually was Max Planck. And the reason for that is totally obvious, because for him, those discrete distributions, they were physical reality. And therefore, it is in 1913, in the second edition of his book on propagation of heat, he explicitly introduced this very entropy. And he was the first to have done it. And he writes about it quite in detail. For instance, in his Nobel lecture, Max Planck really describes in quite detail how he came to realization that entropy is a function and not a cocycle. Because once again, when one was talking about physical distributions, really what matters was the, as always happens with when dealing with differential entropy, what mattered was really just the increment. So it was really a cocycle. And it was for Max Planck, because of this quantum theory, that one had to set a certain absolute level. And that's how he introduced really this entropy. So in my opinion, it should be associated with the name of Planck. Now, John von Neumann, of course, was perfectly aware of the work of Planck, and later in, so, okay, Planck, 1927. Von Neumann, who was perfectly aware of the work of Planck, and of course introducing his quantum entropy, he actually was explicitly quoting the corresponding definition of Planck. And now in what concerns Shannon, his famous communication theory appeared in 1948. Shannon actually, he didn't make any priority claims concerning the definition of the entropy. More or less, he explicitly mentions that this entropy had already been known at the time in, let's say, statistical mechanics. And, well, maybe it's certain limits of the horizon of, well, ultimately he was addressing engineers in his book, so that he didn't really want to bother them with too many details. And unfortunately, later people who well, only read Shannon's paper attributed that notion to Shannon himself. There are even I would say completely responsible anecdotes which are quoted in various books, like allegedly Shannon actually himself didn't confirm that allegedly Shannon had a conversation with von Neumann, and von Neumann suggested to him to use this word entropy because no one allegedly knows what it is, and therefore you would always have an advantage in any discussion. That's entirely unrealistic. Okay, so now what the difference that Shannon made, and he made a lot of difference, in particular, he did introduce a new entropy, and that's what should have been called Shannon entropy. Namely, he considered the following situation. He looked in his language at a stationary dynamical system. Okay, so X1 and so on is a sequence of symbols from a certain, let's say, finite alphabet. Well, that was his model of the information transmission, model of communication theory. And then what he did was the following. He looked at the entropy of the joint distribution of the first n letters in this stochastic infinite stream of symbols. And then he noticed that if one looks the entropy of this joint information of this joint distribution, in other words, the amount of information contained in n symbol from a certain stationary stream, then if you divide it by n, there is a limit. Well, the mean specific amount of information per symbol in this stream.
Is it important that they are the first?
Huh?
Is it important that they are the first, or any n?
No, it's stationary, so any chunk of n consecutive symbols, no matter where, because it's stationary in his model. So that, therefore, if one passes to a limit, if one lets those sequences of symbol getting longer and longer, then one obtains the asymptotic entropy. That's what should really be called Shannon entropy. This asymptotic entropy. And it is this asymptotic entropy which, of course, plays really the central role in Shannon's information theory, because, well, this asymptotic entropy measures, well, capacity of channels, so how much information can be transmitted, and so on. It is all in terms of this asymptotic entropy. Okay, now, as I said, Anatoly Moiseyevich, he started this big program of looking into asymptotic characteristics of groups, and he actually had the idea of carrying this over to more general group setting. And I remember very well how he was talking to me about this entropy, and then at some stage, it must be probably early in '78, he came back from Moscow, from one of his trips to Moscow, and he told me he was, well, everyone who knew him, they know he was kind of, he liked to keep different pieces of information separately. And so he told me, without naming any names, that his ergodic friends in Moscow, друзья эргодики, told him about a paper by André Abetz, in 1972, who had actually already realized this idea and introduced the notion of asymptotic entropy for groups. Actually, as far as I could figure out later, this someone in Moscow was most likely Anatoly Mikhailovich Stepin, Professor Stepin. Okay, now Abetz, he did introduce the asymptotic entropy for groups, and the idea is actually very similar to the idea of Shannon. So what happens here? Well, we have one-dimensional distributions. Well, what happens with a single symbol? Distribution of the single symbol. Like, that's what Shannon started from, right? From discussing the first frequencies of individual letters in the English language, then frequencies of pairs of letters, and so on and so forth. Okay, so and then what happens? What happens when one starts to put symbols together? Then the amount of information is somehow reduced. Why? Because the symbols are not independent, right? If we had considered a Bernoulli scheme, sequence of independent symbols, then of course the asymptotic entropy would have been just the original entropy of the one-dimensional distribution. Okay, so this asymptotic entropy therefore provides a quantitative measure of this compression mechanism due to the interrelation between symbols. Okay, so a lot of them taken together, they contain less information than each of them taken separately. That's very well-known effect in information theory. And in the group theory, one can think about something quite similar. Namely, if instead of just taking strings of symbols, we now think about those symbols being actually generators of a certain group. Okay, and then, well, now X are group generators, and now instead of writing them next to each other, we can just, well, we can also write them next to each other, but in a slightly different sense. In the group theory sense, in other words, we can take product of those group generators, or more generally group elements. And then, of course, everyone knows that in principle, if you have sufficiently many, well, group elements can be written as products of generators in many, many different ways, right? And therefore here, well, we also have a certain compression of information, namely, well, we multiply, so each of those generators contributes to this product. However, the product, of course, may contain less information. So that's a similar phenomenon. And then one can make how this amount of information in the product is contracted as n goes to infinity. So that was the idea of Abetz, but surprisingly, although he was, and he states it very explicitly, he was inspired by the definition of Shannon, his definition, honestly, from technical point of view, doesn't look very ergodic and looks, in a sense, if one can apply this very nice French word, looks as a kind of bricolage. And Anatoly Moiseyevich, although, well, now he realized that, well, this definition had already been formulated. However, well, he wanted, as always, to do everything properly. And the proper way of working with entropy was, of course, to use the general theory of the entropy of measurable partitions due to Rochlin. And that's what my task was. I remember one of my first assignments was 78, I think, was to calculate the entropy of the simple random walk on the free group. And then, well, ultimately we developed what later became the entropy theory of random walks. So let me give the rigorous definition of this entropy. So suppose now we have a group, countable group, and a certain probability measure on this group. So that's an analog of one-dimensional distribution in the Shannon setup. And then one looks, okay, let me keep this notation. So now xi are the increments of my random walk. Xi are the increments of my random walk, and the random walk itself consists in their consecutive multiplication. Okay, so let me denote it by yn. So yn is the position of our random walk at time n, and this is really what can be called random walk on a group. That's a generalization of the classical abelian random walk. So that's a Markov chain on the group. What are the transition probabilities? Well, if you are already at a certain point, then you randomly choose an increment sampled from this distribution and multiply by it. So that's precisely the same random walk, which was classically described probably first by Poyas, or a drunk, no, nowadays one shouldn't say a drunk man, a drunk person stands at an intersection of two roads, and then, okay, so I shouldn't say he, they. He becomes, yeah, because he is drunk, he becomes several. Yeah, so, well, they toss a coin, or rather two coins, because that's an intersection, and choose which way to go. Usually, this description is applicable to abelian groups like this, but actually, if we have any group with two generators, then its calligraph locally looks precisely the same, namely, well, there are two generators, two inverses, so at any point there are four different directions to follow. So that's the simplest random walk on the on a group with two generators. Okay. So now one takes the distribution of this position of our random walk at time n, which is the same as this joint distribution here, and takes its entropy. Now here the compression mechanism is not because of the interrelations between increments, but just because of the group multiplication. Well, there may be certain cancellations and so on, so some of the information will be lost. And then, therefore, if we look at the entropy of the corresponding one-dimensional distribution at time n, that's precisely the n-fold distribution of the measure mu with itself. That's how one defines convolution, actually, because convolution is naturally defined for measures, not for functions, contrary to what mathematical physics would say. And then this converges to the asymptotic entropy. Converges to the asymptotic entropy. And now there is a certain difference. There is a certain difference which is the following. Well, first of all, from the point of view of ergodic theory now, if we go one level higher, suppose that we have a certain dynamical system, measure-preserving dynamical system. A priori, of course, there is no alphabet associated with this system. How do we introduce such an alphabet? Well, we have to introduce a certain partition, or generating partition, which is what? Which is, we have a state space, we subdivide it into pieces, A1, A2, A3, and then we follow trajectories of our dynamical systems, but at each step, instead of giving the precise position of our particle at the corresponding moment of time, we just record in which of the elements of this partition our particle belongs. And like this, we obtain, therefore, a sequence of letters. So in this case, those letters are 1, 2, and 3, or symbols. And that's how one realizes our originally just measure-preserving transformation as a symbolic dynamical system. That's very common construction in ergodic theory. Partition, if actually like this we don't, if any trajectory can be restored just by looking at those names of the domains that it passes through, it's called a generating partition. Okay, so here this Shannon entropy, this asymptotic entropy, is only defined with respect to a certain partition. Well, then one can additionally require that this partition be generating. And then, well, concerning, as far as ergodic theory is concerned, it is Kolmogorov and Sinai who actually noticed, who gave definition of the entropy of a general measure-preserving system, which in particular coincides with the entropy of a generating partition. And therefore, from the point of view of ergodic theory, this entropy of, with respect to a given partition, also plays certain technical role, So, on the other hand, in the group setup, it turns out that, well, there is no underlying more general system. So here we're having that partition from the very beginning, and actually this quantity, the asymptotic entropy, has very important qualitative property, namely this entropy, assuming that the original entropy is finite, the asymptotic entropy vanishing has important qualitative property. It means precisely that the random walk has no non-trivial behavior at infinity, or, which is the same, no non-constant bounded harmonic functions, or which is also called the Liouville property. Okay, so now, oops, yes. Okay, so now the first comment which I would like to make is the following, that actually those two definitions, the asymptotic entropy of Shannon and the asymptotic entropy of Avets. They considered to be very similar, those definitions very similar, or maybe even parallel, but they were considered completely separately. But actually there is a very nice way to treat them in a completely uniform way. So there is a unifying theory, which is the following. So let me formulate this general setup, which contains as particular cases both Shannon entropy and the Avets entropy. That's the following. Let's start with a group. And then consider, instead of a sequence of independent group-valued random variables, let's consider just an arbitrary stationary sequence of increments. In other words, in the language of random walks, I'm now talking about random walks whose increments are not necessarily independent, but they're just stationary. And of course, there is nothing new in this setup, because one is very well familiar with the products of, let's say, stationary random matrices in the multiplicative ergodic theorem, for instance, and so on. However, for some reason in the discrete setup it hasn't been considered. And then, okay, what I'm going to do, I'm going to consider, therefore, this random walk with stationary increments. And then, what do? I still have the common distribution, h of yn. Which, it's easy to see, if I take the sequence of these entropies of one-dimensional distributions, this sequence will be subadditive, and therefore I will obtain a certain limit which should be called asymptotic entropy. So why does it contain both Shannon and Avets definitions? Well, Avets, that's obvious, because here it is enough to take just xi's to be independent. So in the case of independent increment, that's precisely the one. And what about Shannon? That's also very obvious from the group point of view, but no one thought about it this way. So here what one should do, which group shall one take in order to obtain the definition of Shannon? Well, there we are talking about strings of symbols, and therefore the group which one should take is just the corresponding free group, or rather even free semigroup just generated by these symbols. And then what is the multiplication? The multiplication is precisely the concatenation of symbols. That's what one does in the definition of Shannon. So now that we have this generalized setup, I think that it would be really interesting to look also, to look again at the asymptotic entropy from this more general point of view. So I can say, for instance, that one can prove the Shannon-Macmillan-Bryman theorem for this entropy. However, and everyone familiar with the classical entropy and the classical Shannon-Macmillan-Bryman theorem knows that it's not so easy to prove, because one cannot use the subadditive ergodic theorem. Subadditive ergodic theorem only works for independent increments. So here one has to be more technical. And then, of course, there is a lot of questions one can ask about various other qualitative properties of this asymptotic entropy, especially concerning the analogs of the ones that we know in the group case for the entropy of Avets. Once again, in what concerns ergodic theory, there was not really that much attention paid to, well, the entropy of, well, this Shannon's entropy per se. Because in the modern theory, it's just an intermediate step to considering entropy of transformations. Well, I'm aware only of one, well, relatively recent paper by Professor Gurevich, in which he looked at what happens with this Shannon entropy when the one-dimensional entropy is infinite in certain situations, but okay, I won't go into further details. Okay, and now what I wanted to say, so I have about 10 minutes more, right? So what I wanted to say is another illustration of the qualitative effects associated with this notion of entropy. So here I will be talking just about the random walk entropy. And there, as I have mentioned, one of the properties of the asymptotic entropy is that assuming that the original measure has finite entropy, under this assumption, the asymptotic entropy is 0 if and only if the random walk has a trivial Poisson boundary, no non-trivial behavior at infinity, or in the analytic language, actually one can formulate it without saying a single word from probability. That's the same as saying that the sequence of the convolution powers of our measure converges to left invariance. Converges to left invariance. Okay, that's fine. So what does it mean? Essentially it means the following. So if you take the sequence of convolution powers and start shifting them by a fixed element of the group, then the result asymptotically is the same. Those measures in variation will asymptotically be the same. Now, if instead of our original measure mu, I now take the reflected measure, then what happens? The entropy actually doesn't change, right? Because, well, if I convolve this one with itself n times, it will also be the reflection of this n-fold convolution here, so that the n-fold entropy of the reflected measure and of the original one, they have the same entropies, and therefore the asymptotic entropies also coincide. And then it implies the following somewhat unexpected property. Therefore, it means that under this condition, top left, that the entropy of our distribution is finite. Then, under this condition, convergence to left invariance of the convolution powers is equivalent to the convergence of the same convolution powers to the right invariance. And here, well, the conclusion is really an entirely qualitative property, which doesn't say anything about entropy. And for some reason, entropy does appear here. And it turns out that actually this condition is essential here. Namely, there exist groups and measures on them which have infinite entropy, and for which convergence to the left and to the right invariance, they are not equivalent. So there are a sequence of convolution powers such that this sequence converges to invariance on one side, but not to invariance on the other side.
You meant implies, not equivalent, right?
Huh?
H of mu is less than infinity implies.
Yes, of course. Yes, yes. Thank you. Yes. Okay, it's easy to erase. Yes. Only in one direction, of course. Only in one direction. Okay, so this example, I actually constructed it more or less at the time when we started this program in the late 70s. Let's say 80 something. Okay, and today I want to describe yet another example of the same kind, where for some reason the appearance of entropy leads, of finite entropy leads to unexpected qualitative effects. So that's let's look at the following situation. So now I will take the product of two groups. I will take the product of two groups, and I endow this product with a certain measure, which is not necessarily a product measure. That's important. Just a certain measure. Okay, and then the question is the following. So I can either look at what happens on the group G with the random walk determined by my joint distribution, or I can use at the marginals of my measure on the first group or on the second group. Okay. And a consequence of the entropy theory is the following, that actually it turns out that the behavior of my random walk on the whole group, well, behavior at infinity in the stochastic sense. So here, strictly speaking, I'm talking about the Poisson boundary. Okay, so the Poisson boundary of this big group endowed with the measure mu will actually be completely determined by the behavior of the two marginals. So what happens if I project on the third group? There is a certain boundary behavior. Then I look at the projection on the second group. There is also a certain boundary behavior and nothing else, and nothing else. And this result is also satisfied when this result is also true when the entropy of the step distribution is finite. So if then we can identify the Poisson boundary of the big group with the product of the Poisson boundaries of the group's multipliers. And it turns out that here again the presence of entropy is actually critical. It is critical, and namely there are examples such that necessarily the step distribution has finite entropy. And then, for instance, one may have the following situation. So if we look at each of the projections, then there is no non-trivial behavior at infinity. The Poisson boundaries are both trivial. But the Poisson boundary of the whole big group is non-trivial. And that's actually the first example when measures with an infinite entropy provide us with a behavior at infinity which is different from the behavior which we observe for finite entropy. So my last sentence is that I have to mention that Andrei Alpeyev, also a student of Vershik, actually having learned about my examples, he showed that actually this is a pretty general phenomenon, and such examples can be more or less constructed for all the groups which satisfy certain reasonable conditions. So those are the groups for which one can have random walks both with trivial and non-trivial boundary behavior. But okay, I guess I have no time for further details. Thank you.
Thank you very much. Questions, please.
What was your example?
My example is based on the lamplighter group. And there the idea is the following. Well, there is a certain measure which I used here, a certain measure which I used here. And then, okay, so what do? I have to build a certain joint distribution whose marginals, I know they don't have any boundary behavior, whose Poisson boundary is trivial, but I can just modify the joint distribution in such a way that, for instance, if I look at the difference between the marginals, then the corresponding random walk will be finitely supported and therefore demonstrate non-trivial boundary behavior. So example is very simple, very simple. The idea is new, but the example is very simple.
Some more questions. Yeah.
That old example was also about the lamplighter.
Yes. So, well, unfortunately, I didn't have time to describe the details, but it's all pretty simple probability.
Just one side question. So you talked about discrete groups, discrete case. But is it possible to define the same thing like a measure or like entropy for algebras?
For algebras, not groups. Not sure. Somehow I had thought about that, but somehow nothing meaningful. At least I couldn't produce anything meaningful. Yeah.
But in addition, does it matter in this way that it's when you define these four groups, you need it to be a group or just a semi-group?
Okay, that's okay. What one needs, first of all, of course, semi-group will also be okay. Now, whether it's semi-group with cancellation or not, I'm not quite sure. Probably one would need something like this. So I'm more comfortable to talk about groups. On the other hand, if we want to go further into algebra, groups can easily be replaced with, let's say, groupoids. But it's still not semi-groups. Yeah.
Is there a version of any of these theories with infinite time, where instead of discrete parameter 1 through n, you have a continuous parameter t, and so you get like a stationary process in the group?
Continuous time here doesn't really make any difference, because the purpose of all this activity is to understand what happens at infinity. And from the point of infinity, those tiny time intervals, they don't really matter. So let me put it this way. If you have continuous time process, then you can, of course, always make it discrete time, just by looking at, let's say, integer times. And as far as behavior at infinity is concerned, it's much easier to deal with discrete times. It doesn't change anything, really, the fact that time is continuous. it may be easier to obtain certain expression by using like generating operators, expressions for asymptotic qualities. But qualitatively, no, it doesn't change anything.
Sorry, I should stop the discussion. So, okay. So, thank you.
Thank you.